In this video, we're going to talk about Gibbs free energy, which essentially determines whether or not a reaction can be spontaneous. So a spontaneous process happens with no net input of energy. That doesn't mean there's no activation energy. Spontaneous reactions still can require some energy to get them started, but the net result is that more energy would be released than energy required to be put in. So there's a net loss in energy, and that energy we're calling Gibbs free energy. Now, exothermic processes make sense that they could occur because you know they give off heat to the surroundings. However, endothermic processes can still be spontaneous. Okay? But that's because there's something else in play, and that something else is called entropy. Now, entropy is incorporated into Gibbs free energy equation. The delta G, which is Gibbs free energy, is essentially the energy available to do work to the surroundings. So in order for a reaction to be spontaneous, it has to release energy to the surroundings, and that is right here. And it would have to be negative for it to occur. It incorporates both the enthalpy change of a reaction, which has to do with the change in heat content of the system, so essentially the thermal energy. And if delta H is negative, that means it's releasing energy to the surroundings, okay, which is a favorable state. It's dispersing the energy. The other thing we said is entropy, which is essentially you can consider the disorder of the system. But what it really means is the possible number of matter arrangements you could have. So the more disordered something is, the more possible matter arrangements there are. So you have energy dispersal accounted for in your enthalpy, and you have your matter dispersal accounted for in your entropy. So entropy is also multiplied by the temperature here in Gibbs free energy equation. So let's take a look at some situations and see whether or not a reaction can be spontaneous under those conditions. So if the reaction's exothermic, that's favorable. If delta S increases, meaning the entropy increases, that's also favorable. So both of those combined mean that the reaction's going to be favorable, and it's likely to make product, which means it's going to be product favored or spontaneous. The next situation we're looking at is that an endothermic system requires an input of energy, and that's not necessarily favorable. So for that to happen, it has to be compensated for by a large increase in entropy. So if the entropy actually goes down, okay, this term essentially, because a negative times a negative makes a positive, this becomes positive, this is positive, delta G would be positive, and it would be reactant favored, which means it would not be spontaneous. Now, when you have one thing that's favorable and one thing that's not favorable occurring, that means we have to take a look at what the temperature's impact is. So when you have an exothermic process that has a decrease in entropy, or you have an endothermic process with an increase in entropy, those are going to be temperature dependent. Because the larger this value is, the more it magnifies the impact of the entropy change. So for the last example, where it's endothermic, which is not favorable, but the entropy increase, which is favorable, the higher the temperature is, the bigger this term becomes, and essentially can overcome the fact that it's endothermic. And we saw that happen in the reaction that we did yesterday, where I froze the wooden block to my Erlenmeyer flask. If it's exothermic, however, which is favorable, but the entropy change is negative, which is not favorable, we want to minimize that impact. So the reaction is only going to be spontaneous when this temperature value is low, meaning that the negative value of the enthalpy change will outweigh the negative change for the entropy. So those are our situations. We want the reaction to be releasing energy in order to be able to happen. Now, we can calculate Gibbs free energy in a number of ways. One is we can use Gibbs free energy equation if we're given the enthalpy change for a reaction, and we're given the entropy change of the reaction, and we're given the temperature. We can determine whether or not the reaction will be spontaneous. So the other way we can do it is just like we did with heats of formation. We can calculate the Gibbs free energy for a reaction by subtracting the Gibbs free energy of formation of the reactants minus the product. So you would need a table of values for this in order to do that. So let's take a look at one of these. This reaction right here is the burning of acetylene, which is what we use in welding torches. And you would imagine that would be very exothermic. It releases energy. You're able to weld with it. However, you actually have more moles of gas you have 3.5 moles of gas in the reactant side and only 3 on the product side. So it actually goes down in entropy. Now, we could calculate at 298 whether or not this is going to be spontaneous. So what we would then do to calculate delta G for the reaction, we would essentially plug in our enthalpy change And we would make sure that we report our entropy change in kilojoules per Kelvin so that we're comparing apples and apples. Usually it's given in joules per Kelvin, so convert it to kilojoules per Kelvin before you plug it in. But once you plug it all in, you can see that you still have a net loss in energy, and Gibbs free energy is negative 1209, which means it's spontaneous. And we know that that would be spontaneous because we can do it. The next type of calculation we can do is if we're given the tables. So here we have a reaction, the burning of methane, which is what we use for our Bunsen burners, in oxygen to make carbon dioxide and water. And we just have to use the tabulated values, and we subtract the reactants from the products, because anytime you have a delta, that means it's the change, which is always going to be products minus reactants, or final minus initial, because the products are our final matter states, and the reactants were our initial ones. So we just plug in the values. So we had 1 CO2, and we can see that the value is negative 394.4 kilojoules. We have 2 carbon dioxides, so we plug in those values, and we subtract the reactant value, and we end up with the Gibbs free energy for this reaction, which we also know is spontaneous because it can happen, of negative 817.9. So those are the two ways we can calculate delta G. If it's negative, it means the reaction is spontaneous, and it can proceed with no net input of energy.